Today we're going to be talking about our aromatic toolbox, that is, all of the different reactions we can use to react benzene and substituted benzene rings to convert it to one to the other. This is an overview of reactions that occur primarily in Chapter 22, but also in Chapter 23 of your CARDI textbook. First, of course, we have our electrophilic aromatic substitutions that we looked at last week. That is, we can put halide, nitro, sulfate, alkyl, and acyl groups directly onto a benzene ring. For example, if we use iron trichloride and chlorine, or iron tribromide and bromine, we can put the corresponding halide on the benzene ring. If we use nitric acid and sulfuric acid, we can put a nitro group onto the benzene ring. If we use fuming sulfuric acid, that's sulfuric acid with excess SO3, we put the hydrogen sulfate group onto the benzene ring. And if we use an alkyl halide or an acyl halide in the presence of aluminum trichloride, we can put an alkyl group or an acyl group onto the benzene ring. These last two reactions are called Friedel-Crafts reactions. For alkylation, Friedel-Crafts alkylation, we have to worry about cation rearrangement, but not for acylation. And neither alkylation nor acylation will work with moderately or strongly deactivated groups. Now, this is a nice start for putting a number of different functional groups onto a benzene ring, but it is somewhat limiting. It does not allow us, for example, to put an OH to make a phenol or an NH2 to make an aniline. We can get to some of these groups through redox reactions, oxidation or reduction. In particular, if we have an alkyl group or an acyl group and we treat it with KMNO4, we convert the initial alkyl or acyl benzene to benzoic acid. No matter how many carbons there are in the R groups attached, they cleave completely, oxidizing at the benzylic position only. We could also take an acyl group and reduce it using the reducing conditions we've seen under previous chapters. In addition to normal zinc-mercury amalgam reduction or Wolff-Kieschner reduction with hydrazine, you can also use hydrogen and palladium. This is the only key type of carbonyl that will reduce with hydrogen palladium directly, conditions that normally reduce only C-C pi bonds. But if the carbonyl is conjugated to a benzene ring, it will be reduced with hydrogen and a catalyst. So now we have a different way of reaching into our synthesis. In particular, if we do direct Friedel-Crafts alkylation, we will get rearrangement, and we cannot make primary alkyl groups directly on a benzene ring. But we can get there indirectly by doing Friedel-Crafts acylation, creating an acyl benzene, and then reducing it down to a primary substituted benzene ring. On the other hand, we have no direct way of making carboxylic acids, benzoic acids, but we do have an indirect way by either doing alkylation or acylation and then oxidizing. Another functional group we don't have direct access to is aniline, an NH2 group on the benzene ring. But we do have a group that has a nitrogen already, and that group is the NO2 group. If we reduce the nitrogen atom, NO2 group, we can create aniline, NH2 on a benzene ring, and that's done with a variety of different reagents, but most simply just with hydrogen and a metal catalyst. There is also a series of other reactions we can do, starting with aniline, which could be created from nitrobenzene. We can change it into an aniline group, and then we can change the NH2 group into a diazo group. The diazo group is very useful in that it is basically nitrogen triple bond nitrogen, and when it leaves as nitrogen gas. It is an excellent, outstanding leaving group. And it can be replaced using some redox chemistry directly by a variety of different substituents, including cyanide, chloride, bromide, iodide, fluoride, OH to make phenol, and H. So, for example, if you have a copper salt of the cyanide, chloride, or bromide reaction, these are reagents developed by a chemist named Sandmeyer, so this is often called a Sandmeyer reaction. You end up with the corresponding substituted cyanide, chloride, and bromide. Now, of course, we can already put bromide and chloride directly onto a benzene ring, but there will be times that for reasons of directing group effects, we want to put that group in a different position than would naturally occur. And the Sandmeyer reaction can help us for the chlorides and the bromides. It is also the only way we have to put directly a cyanide group onto a benzene ring. We also can use the diazonium intermediate to create iodobenzene and fluorobenzene, compounds that are not directly accessible through electrophilic aromatic substitution. One very important functionalized benzene is phenol, that is benzene with an OH directly attached to the benzene ring. And phenols can be created from diazonium intermediate simply with acid and water. And finally, there will be times when we want to remove a substituent from the benzene ring, and we can do that through a diazonium intermediate with hydrogen phosphide or sodium borohydride. We don't normally work through the step-by-step mechanisms on how this replacement takes place. With most reagent, it involves contribution of an electron to the carbon-nitrogen LUMO, which will make that bond even easier to break. The N2 leaves, leaving a radical behind that reacts with our resulting reagent that replaces the diazonium. We do, however, have a very straightforward mechanism for the conversion of an aniline, NH2, to the diazonium group. This reaction happens when aniline is treated with sodium nitrite and a strong acid. Sodium nitrite is, of course, an ionic compound, and a valid Lewis acid structure for the nitrite ion is shown here. In the first step, the nitrite ion grabs onto one of the protons from the mineral acid to make a neutral nitrous acid. Nitrous acid now has a polar pi bond, not too dissimilar from a carbonyl, with a delta plus on the nitrogen atom. Aniline is a good nucleophile and can add to the polar NO pi bond, much the way things add to carbonyls. This creates our first intermediate. In solution, of course, any of the nitrogen and oxygen sites can be protonated or deprotonated. And if we lost a proton off of nitrogen and gained a proton on oxygen, we'd end up with our first neutral intermediate. But of course, we are in strong mineral acid, and so any of the sites can be protonated further to make a positively charged ion. One of those sites is an oxygen atom. We now have a good leaving group, and as water leaves, we can draw the second bond between the two nitrogen atoms. Again, any of the sites on the nitrogen or oxygen could be protonated or deprotonated. One possibility is that the NH is deprotonated to become neutral and the OH is protonated to become positively charged. This would create yet another good leaving group, which would leave with the help of a pair of electrons from the nitrogen. This creates the diazonium key intermediate.